Okay, so our second speaker is Jorg Grosse from OneSpin Solutions. He's the product manager for safety critical solutions. The title of his talk is Formal Fault Analysis for ISO 26262 Fault Metrics on Real World Designs. Jorg is a product manager for functional safety at OneSpin. He has more than 20 years experience in EDA, functional verification and ASIC design. As co-founder of a successful Silicon Valley startup, Jorg was central to developing the concept of fault mutation testing into a state-of-the-art EDA tool. He deployed this technology in many leading semiconductor companies, increasing the quality of their functional verification. Jorg holds a diploma in electrical engineering from the University of Applied Science in Anhalt. Can you unmute yourself as well? We seem to have a common problem today.
Sure, here you go. Can you hear me well? So I assume you can hear me. So thanks a lot, Mike, for the introduction, and also thanks to Anne. There was a really good introduction to the overall functional safety and the flow. So what I would like to do is drill down further into a real use case, and I'm going to take the EXA Crossbar and we'll show you how we do functional safety verification on that EXA Crossbar. So just a small recap on the high level flow. On the one side, we have our systematic errors. We minimize them, or our goal is to minimize them through pretty much a standard rigorous verification flow. On the other side, on the right-hand side, we have to safeguard against the random errors. And in order to do that, we come up with a safety architecture. First, we have obviously our safety requirements and our safety goals. We derive a safety architecture from that and the hardware safety specification. With that, we are going to implement our hardware or software safety mechanisms, and then eventually we have to verify that the safety mechanisms work correctly. We not only have to verify that those safety mechanisms work, we also have to do what's called the FMEDA. We already talked about that in detail. If we have derived our FMEDA, what we also have to do is kind of an association. So we have to see which failure modes are attached to which parts of the design to eventually derive something like a fault area information. And once we have this fault list, which corresponds to our safety mechanism implementation, then we can do our diagnostic coverage verification. And I'm going to talk about the verification of the safety mechanism and the diagnostic coverage verification of the EXA Crossbar. So in terms of safety mechanisms in general, we typically divide them into software and hardware safety mechanisms. The software-based safety mechanisms, or also people call them software self-tests. So basically, we have a test program periodically running, and this test program should make sure that our chip is still functions correctly. This typically requires fault simulation, but we can also apply some formal methods to understand how to propagate faults, or if they can propagate at all in the context of this software self-test. What I would like to talk about today is more hardware-based safety mechanisms. So the characteristics of hardware-based safety mechanisms are that there is a mission function. Then we have a safety mechanism around that mission function. That safety mechanism has to observe an unexpected value and should raise an alarm. And optionally, we can also have an error correction in place. So we would set a corrected flag and our output would be not impacted under this case. We have an application called fault detection analysis, and that helps us to investigate those hardware safety mechanisms. So now coming to the EXA Crossbar. So it's basically an AMBER fabric, two master, two slave ports, separate read and write logic, configurable FIFO, and we have a single clock domain in this case. And in this case, we had no functional safety mechanism in place. So now, for example, as a designer, we get asked to add a functional safety mechanism because we want to use this EXA Crossbar inside an automotive chip. So what we decided here is to add Parity Protection. And we used a tool from Austin Temper to do hardware safety mechanism synthesis. So we automatically injected the parity protection logic, but you could have also done that by hand. So so once we inserted the hardware safety mechanism, the first thing you have to do is to verify that the original function has been maintained, or in other words, that we don't have broken our design. We can do this by applying combinational sequential equivalency checking, and we have done that with by simply reading the original and the design with the safety mechanism, the inputs and the outputs, and we do a compare. If we do this without any additional setup, what the tool will tell us, the designs are actually not fully equivalent because they are unmapped outputs. So actually the alarm lines we have introduced by adding the safety mechanism. And if we ignore those additional alarm lines and we run our compare, what comes out is that the designs are equivalent. And therefore, we have done the first verification step, which ensures that we haven't broken the design or we have maintained our design functionality. So the second and more interesting step is how do we make sure that the safety mechanism works and we are achieving the diagnostic coverage. So what we have to do here is essentially injecting a fault and see if the fault propagates to an output port, and whether it is detected by the hardware safety. If we do this inside our fault detection analysis, what we have to give to the application is obviously we have to read the design. We also need a set of observation points. The observation points are actually the ones where the fault can become dangerous. So it's associated with our failure mode. Then we have the diagnostic points. So where would we observe a dangerous fault? Then also we need a fault list, and we might supply some input constraints. If we give those inputs to the fault detection analysis, it generates a report classifying the faults we given it inside the fault list into dangerous detected, dangerous undetected, or non-propagatable faults. So what could happen is also that the fault simply gets stuck in the design and it can't propagate to an observation point nor a diagnostic point. So how does it look like in the real world? First of all, we defined our observation points, which are the output ports of the crossbar, without the safety lines, which we actually put into the diagnostic point. Include the faults which are only under the diagnostic points because there cannot be dangerous in a sense that in the sense of the single point fault metric. Those faults under the diagnostic points would be only used for the latent fault metric. And in our case, we want to calculate a single point. So we take those inputs and put them into our detect faults command. And if we run that, what I did here, I took only a sample of 10 faults to speed it up. What comes out is that all the faults we injected are actually non-detected. So non-detected dangerous. So they can propagate to an observation point, but we haven't seen any diagnostic. So that's what we obviously not expected, because as you can see here, we are injected faults onto the FIFO, and we would have expected with the parity protection of the FIFO that those faults would be detected by the safety mechanism. So in order to help us to understand what's wrong, we can debug single faults in the tool. And if I call this command, I'm getting a trace. And what we can see here is that as soon as the fault is active, we color the line in red, which means in the original design, this value would have gotten to 1, but the fault caused it to stay at 0. And now you can see nicely how this fault is actually propagating through the design and eventually reaches an output port, an observation point. And we have seen no diagnostic, which is confirmed by this waveform. If we look a little bit deeper into the trace, then we see that we have an input, which is called arrow clear. And this input has been designed to actually clear the safety mechanism. And what has been done here is we forgot to add a constraint that we don't want to clear the alarm. So now we added that constraint, and we can see that the clearance of the alarm is actually tied to 0 or constrained to 0 now. We again see how the fault is injected and starts to propagate through the design into an output port. But now we can actually see that the alarm has been raised 3 cycles later, which means this fault is now a dangerous detector. So if we now rerun our complete analysis of the 10 faults as samples with the constraints, we see that we are now reaching 60% single point fault metric with this given safety mechanism. If this detection is, or this diagnostic coverage is not high enough, then obviously we could add more safety mechanisms to the design and iterate through this loop, through this verification. This brings me to the end of my presentation. Thanks a lot for listening, and I'm open for questions.
Thank you. Let's see if there are any questions. Any questions in Bristol? No questions online either. Let's check with Cambridge and Grenoble. Any questions?
There's no questions from Cambridge.
Okay. So thank you very much, Jorg, for your presentation. Obviously clear enough for everybody to understand without questions. So thank you. Thanks, Jorg.